Okay, I did update the Piazza post just now. Hopefully people will see it. I'm gonna give it like a couple of minutes for people to transition over. And let's use the off-topic chat on Discord, not the general one. Choppier. Well, it might be choppier because I'm using the ultra low latency mode. Yeah, I'm gonna guess YouTube is being YouTube. Well, this is gonna be recorded, so you can watch it later. I'm trying to watch the stream through mobile, and it's still not. So, Nick, can you hear me right now, or do you have some weird, huge delay? Yeah, I tried to go through my mobile. It doesn't seem to be working very well. Wait, so you guys get audio but no video? Yeah. I think maybe I'll just go continue with whoever is here and can watch it, and then the rest will just have to watch it. Once the recording goes up. Oh yeah. What if YouTube doesn't record it? Hmm. Yeah, people are saying maybe we should switch to Twitch. I don't know. Okay, I see more people joining the stream, or at least reporting it as working. So maybe we'll wait 5 more minutes. Maybe YouTube will fix its stuff. Honestly, Jonathan, I have no clue. I haven't streamed on Twitch for like close to a year now. I don't know what to say. Yeah, YouTube seems to be out in most of the East Coast. Nice. Freaking nice. Oh, I see another Greek name in the chat. Nice. Ezra, I'm pretty sure I'm recording right now, but let me make sure I'm recording it locally. Okay, let me mute the audio really quick so you guys don't get some random feedback. Okay, yeah, I am recording it locally as well, so guess I'll have to test that and upload that if YouTube doesn't work. Okay, I think we can at least try to get started. I don't know what else to do at this point. I guess worst case scenario, we'll just have to redo this maybe. Oh well, yeah, let's get started. Okay, so let me collect my thoughts again because I completely lost my game plan. Okay, so the plan for this session is gonna be, if you have questions, ask them in the YouTube chat. But I think you need to be logged in to type on that thing. So I'm also gonna be monitoring the off-topic channel on Discord. So use either of those to ask questions at any point. First, I will be going over some theory. We'll start with something that we did for the first session and people still do not believe it's true. So we'll start there. Then we'll see some of that theory in practice with a demo I have here with a very stupid file system. And then we'll move on into the VM and see some Fuse related things. It's mostly gonna be about setup and stuff like that, because figuring out Fuse is part of your assignment, right? So I'm not gonna be explaining everything. Okay, so any questions there? Anything before we start? Okay, gonna take that as a no. Oh, first things first. Any file system is made up of two main parts, at least conceptually. The raw data, and then the, let's call it driver. Basically, you have the data and you have someone who knows how to read that data. In your book, for example, it describes a few file systems. I don't think I'm not sure if it talks about specific file systems like FAT32, but I know it describes the notion of FAT. FAT stands for File Allocation Table, and other common schemes or schemes. Anyway. So yeah, if you have some data, right, if you have some bytes actually, let's say that this is our raw binary data, right? Your file system is going to use this area to store things. Now, those things depend on the actual file system. So FAT related file systems have the actual, what's it called? The actual table, the actual FAT table. And then you have maybe directories, you have superblocks, you might have linked lists, you might have AS tables, you might have a bunch of things. So when you're designing, I'm sorry, when you're designing a file system, you come up with a scheme or SIM or whatever, and you say, okay, the first X amount of bytes is gonna be something. The next byte is gonna be something else. Then this is how we describe a directory. This is how we describe our table. And on and on. So for our stupid file system, let's say that we just have raw data, one after the other, and the layout of our data is the first byte is gonna tell us whether this file is used or not. Right? So we have one byte here, and this is whether it is used. The next 2 bytes is gonna be a sort, a uint16, and it's gonna tell us the size of that file. So we have 2 bytes here. And then we're gonna have size bytes after that, indicating the contents of the file. So this thing here is the contents. And so this is size in length. Ugh, someone can only watch in one spot. Yeah, okay. Okay. That's not gonna be very helpful. Can I zoom in? No, I cannot zoom in. Anyway, so this is the layout of our file system, and we just append those collections of bytes one after the other to create multiple files. So the next file is gonna start here with its first byte, then the next two bytes, then a random assortment of bytes, and on and on and on. Now, this interpretation of these bytes is something that we agreed. Actually, I came up with while preparing for this thing, and you agreed. Anyway, right, so again, it's just something that we decided. It's not fixed. So when Microsoft was designing FAT16, they came up with some scheme and they were like, yeah, this is how it works. When they designed NTFS, they came up with some scheme and they were like, yeah, this is how it works. Same for any file system in the world. Okay? So if we want to interpret these data, these bytes, these raw bytes here, we need some logic that first goes check the first byte, sees if that thing is used, then checks the second size byte, sees how long the thing is, then reads the rest of the bytes, and then moves on to the next entry. Now, as a system, this is very, very weird and very, very stupid because you cannot, if you deallocate a file and set the used byte, so if it's used, it's 1, if it's not used, it's 0. If you set it to 0, that doesn't really mean anything. You need to do a lot of work to figure out the rest of the data. But again, this is just for an introductory example. Okay? So, any questions so far? I see some typings here. Okay. FAT32 and FAT16 are just file systems. We don't really care what they mean or how they work. It's just an example file system. And your book definitely covers FAT related file systems. I don't know how, I don't remember how deep in detail it goes though. Well, FAT matters because the file system you are implementing is derived from the FAT, from the file allocation table of structures. Yeah, it talks about FAT in general, FAT, but sure. That's the concept of FAT. That's only you need to care about. The details about how the system we gave you works, the file system we gave you works, is in the project description. Well, yes, you will make your own file system, but we have given you the design of the file system. You do not need to decide how it works. We've given you how it works. Okay, so let's see some of the examples. Right. In here, I have this file system that I just described in a little bit in a prettier format, let's say. So let me make this a bit bigger. Ooh, that might be a bit too much. Can you guys read the screen? Okay. So, as I said, 1 byte for to say whether the file is in use or not. That's pretty bad design-wise, but sure, let's go with that. Then 2 bytes to show how big the file actually is, and then size bytes for how many for the actual contents. In here, in my example, the contents are just text, just so we can print it easily, but it could be literally anything here. It could be colors in byte format, it could be pixels. All right. And a reminder that this part, hello, okay, that this part is dynamic, and it's however many bytes you read from here. Okay, so I can tell you that this file system right now contains 3 files, one of size 13, one of size 15, and one of size 11. No, you cannot download the code because this code will not help you in implementing the project. I'm not going to give you any code that is project related. This code is just for you to understand the concept. Right? You cannot get this code and as it is put it into your system and do things. It's not going to work. Okay, and let me move down here, those down here. So these are the bytes that make up the file system. I've split them up into groups of 8 bytes. So this is 8 bytes. This is another 8 bytes. I did it for no particular reason. It's just that hex viewers sometimes split them in groups of 8 or maybe groups of 16, groups of 4. So I did that way. Those bytes can be coming from anywhere. They could be coming from a file, from a disk, from anything, pretty much. For the simplicity of this example, I'm just defining them here. Okay, so remember the structure of the file system. Okay, so first file. We know that the first file is of size 13. Just by looking at these bytes, can you guys tell whether the first file is used or not, is in use? Yes, it is because the first byte here is 1. Right? So, next step, what is the size of this thing, of this file? From our description, we know that the size is 2 bytes, so it's these 2 bytes. 0D00. Let me bring up my trusty calculator. So the Windows calculator has this wonderful feature of the programmer. So let's put these values in 0D00, which in decimal gives us 3,328. But we expected the file size to be 13. Okay. This is NDNS in practice. In your x86 machines, that is basically your host OS and your virtual machine, numbers, multi-byte variables actually, are stored in big endian, in little endian, sorry. Okay. Little endian means that the bytes are in a reversed order. So a uint16 with the value 13, normally as humans we would read it as 000D. This is 13 because we start counting from the right. Right? Same as if you wrote it in hexadecimal, it would be, let's say, 0013. Right? Now, when they are stored in memory, your computer flips them around. There is a reason for it. It's backwards compatibility at this point. There is pretty good speculation that even internally, x86 machines no longer do this, but the API needs to do this to be backwards compatible. So instead of storing them as 000D, we have to store them the other way around, 0D00. Now, this is why you might, for project 2, if you were trying to somehow copy bytes from a uint64 into a byte array, this is why you would be getting problems, probably. Because you were copying the bytes in the wrong order. Okay, so these 2 bytes now are our size, which if we put it here, if we delete this and put D, we see that it's 13, the size that we expected. And now we know that the following 13 bytes, you're going to have to trust me that these are 13, are the contents of this file. Okay. So this was our human understandable explanation. Let's do this in code now. Okay. So we have our first pointer. We want to make it point here. We have our file size pointer. We want to make it point here. And we have our contents pointer. We want to make it point here. The file contents also reversed. If the file contents are multi-byte values, yes, they will be reversed. Here they are just an array of characters, and characters are 1 byte, so they're not reversed. Only multi-byte values are reversed. So bytes is a pointer, an array and a pointer are the same thing, right? So our in-use pointer is bytes plus 0. 0 is our offset, right? Since this number is at the beginning of bytes, we do it bytes plus 0. Remember this, we're still dealing with pointers. Most of the time you will want to deal with pointers when you're doing operations like these. Next is the file size. So we know that the file size starts at the second byte, so we need to skip 1 byte. So we do bytes plus 1 to move 1 byte in, and now we cast this bytes plus 1 into a uint16 pointer. We could be casting it into whatever we wanted, right? But we know that we need to interpret this as a 16-bit integer, right? Because we agreed that this is how we're gonna use the system. And then for the contents, it's wherever bytes is plus 3. Why 3? Because we need to skip these 3 bytes to start reading from here. Okay, and then we cast this into a char star. Is this clear? There is a question, how do we know that contents will reach the end of that file? What do you mean? I'm not sure I understand the question. Why not uint8? Because I want to treat it as strings, and I've decided that the contents for this file system, for this example, is char star. Normally you would be treating it as bytes, uint8. I just decided that the files only contain text, so it's easier to demonstrate here. Okay, so for your projects, you should not decide that they are strings. For your projects, they are just bytes, and you will see soon that it makes absolutely no difference. This is what I said since the very first session. Everything is bytes. It's just bytes. All that changes is how we read those bytes. And that's why I said it from the very first session. If you did that for project 1, project 2, and project 3, everything would just be simpler for you. Okay, so GamerXNin, just get back to me when you can clarify this question, and I will return to it. I'm gonna move right now, but please tell me exactly what you mean here, because I didn't get it. Jonathan, we will get to the second file in a little bit. Okay. So if we run this code, actually let's debug it so we can see it execute. Okay, so over here is our memory, the whole memory, including stack and heap. Okay, where is... So let me go to bytes, for example, here. Yes. Oh no, this is a spoiler. Fuck. You did not see that. Okay, so we have a watch window over here, in use, file size, and this is for later. So let's step over this line. Now in use points to something which has the value of 1. because in use points to here, which was 1. And so this seems to be going well right now. Let's step over one more. Now, file size is also a pointer. As you can see here, I don't know if it's visible, but I'm dereferencing those first. And so if I do not read the reference, file size is this number here. It's 009DC001. This is an address. And in that address, you can find the value 13. Okay, I mean, I've tried to explain pointers multiple times. I don't know how simpler to make it. So the value of file size is this number here, this address. And at that address, so if you dereference it, you will find 13. Okay, and we're gonna print this thing out. And let's see the output. Oh, nice. So in use, you get the smiley face because apparently 1 converted to ASCII is this smiley face. Sure. Size is D. This is the hexadecimal value of size. And the contents are hello world. Actually, the contents are hello world, new line, \0, so the null terminator, and then I'm adding one more new line from here. Okay. So let's stop the debugging. Oh, where's my web browser? Here's my web browser. ASCII table. This website is going to be very useful to you for your computer science career. You'll have to reference it multiple times for a plethora of reasons. So let's start with 48. We have the byte 48. Let's look it up here. 48 is capital H. Okay. Then we have the byte 65. Let's look up 65. It's going to be over here. 65 is E. I think you see where this is going. I'm not going to go through the whole hello world. Then eventually we have 0A, which is 10. 0A is the new line. This is why you had to unescape in project 1. In project 1, when someone types \n, you have 2 characters. Okay? You have the \, which is somewhere in here. Let me find it. Here, which is 5C. And the n, lowercase n, which is 6e. So if you type \n, you have the bytes 5C, 6e. But if you want the new line, i.e. the line to go one below, you have to put in the sequence 0A. Okay, this is what unescape was doing with the rest of the quotes and octas and everything else, right? And then you have the 0, which is the null terminator. Okay, so from here to here, you have the string hello world. Okay. Any questions so far? Okay, I'm gonna keep going then. Seems similar to mailboxes again. Well, probably does because that's how your computers work. That's your computers. There's no more to it. That's it. All operations are reading and writing bytes. Okay, so let's go to next file. We made the choice that the next file is going to start immediately after the previous file. Okay, so again, we know that this file is used because that's the structure of the file system that we decided. It's 0x11 for size, so 00x11. This is what you would expect from here. And it has a few bytes in text. So it starts from here and it goes all the way up to here. I can tell because the 0 is here, so this is the end of some string. Okay. And then this is the third file. Yes, it doesn't have to be char. We're just treating it this way so we can print it and you can see it work. Okay, I'll show you how to actually work with bytes and modify the file system manually if you want to through a hex editor later. Okay. So, and this is the third file, which is not used. It's of size 0b, which is 11. And these are the contents. Now, if we wanted to print those, we would have to, calculate the offsets again and do all of that stuff in order to save some time, right? I have pre-written that code. Okay. And let me put a return here. So this never executes. It said never executes. And let me copy the code. Let me copy the whole code. Okay, so I said that we have only 3 files, just to make it faster. So you can't have a null terminator inside the file. Yes, you absolutely can have null terminators. A null terminator is just 0. Now, for this file system that only contains spaces, only contains text, yes, you cannot have a null terminator in the middle of a file. Well, actually, you could. You would just never print that. You would have to adjust for that somehow. Because the size is not relevant to the null terminator. The size is something that we put in. You could have a 0 here, for example, and still read the whole thing. But when you print it, you're only gonna get a print up to here. So this is the code to print all the files. We start with an offset. First, we do the same thing again, bytes in offset, which starts to 0. Dereference that to get our actual number. Then we increase our offset by 1. This is how you should be using sizeof, by the way. Since I know I have one thing here, I'm gonna get the size of that thing. Okay. Then we do the same thing again for the size variable. We increase our offset by the size of 16 now because we just read 16 bytes. 16 bits, sorry. We make our content point to there. We print all of our stuff, okay? And then we increase the offset by size bytes, well, times size of char, which is 1, okay? So if I run this really quickly, there were build errors. You are a build error. Oh, sure, return 0. So file 1 in use 1, size 13, contents hello world. File 2 in use 1, size 15, contents computers tool. File 3 in use. So file 3, even though uses 0, it still has some contents. So you could imagine that you could skip this file, for instance, because it uses 0 for some reason. Again, the offset is just a conceptual thing. If you need to read further, you need to increase that offset. As I said, if you take this code and you put it into your project, it won't work. It won't do anything for you. This is here just so you understand the concept of, okay, I'm going here, reading one thing, moving, reading another thing, moving, reading another thing. Because this is what you have to do in essence to understand the file system. And how you move around, that's the way the file system works. So are there any questions here? In use, absolutely nothing for this file system. That's just something that I came up here for the purposes of the example. You could say that if this is 0, I do not print its contents. Sure. This is what it means. Ryan, I already answered the offset question. So yeah, again, in use is something that I decided. It doesn't mean that the file system that we gave you has an in use or something, right? Again, the whole thing is my decision right now. I came up with this design. Which is a very simple design just to demonstrate some things. It's not a real file system, obviously. Okay, so this is a hex editor. The one I like to use on Windows is HXD. Visual Studio Code also has a built-in, an extension, not a built-in thing, that will convert it into a hex editor, so you can use that, and it has most of this stuff. And then on Linux, you have, an infinite amount of hex editors. You have command line hex editors. You have the one that I will use when we get into the VM is Octeta, which is a KDE hex editor, just because I like that one. You could use literally any hex editor that you want. I don't remember the name of the VS Code extension, but if you Google it through the and search the extensions menu, you will find it. Okay, so let's open up this empty image is a correct meme image, memefs image. Okay, so if you open it up, you just get bytes. All right, does this look similar? So all of this thing to this? Right. I really hope it does. Okay. Now, as you can see here on the right, it says decoded text. most hex editors will try to convert whatever they see into characters. Is anyone out there? Okay, because some people are getting a complete error message, no loading, no nothing. No, Patrick, the in-use byte doesn't really serve a profound purpose. It's just something that I put there, so we have something to read. Okay. You could say that if the thing is 0, I do not print its contents, but that's about it. There is no one telling us what in use means, right? This is very important to understand. The only reason bytes have meaning is because we decide to do something with them. So, for instance, sure, if you would really like to push it, but again, let's say it's permissions of some kind. Not really, but sure. So these are the raw bytes of an image generated by make mkmemfs. Okay, so if you run the program that we gave you, it will generate something like this. If you can see, so this is the very first byte of the file. So as the description says, the first some bytes, I don't remember however many, need to be this string, question mark memfs plus plus CMSC 421. Okay. And as you can see, you have the text here. You could load this file and read it similar to what we did here, for instance. Okay. Then it has a bunch more stuff over here. As you can see, most of those bytes are 0 bytes because they are empty. This is a fresh image, so it doesn't have a lot of stuff. Here we see some more bytes that means something, and you can see there is a myname.txt file in here. So maybe that's a file name that's stored in here. And then scrolling further down, we find that string again on the other block. You have 2 super blocks in the image we gave you. So let's say you wanted to modify the signature in this block. You could literally just come in here and type something in, hit save, and it's changed. As you can see, the context now say ME bracket EFS instead of memfs. Okay. Every hex editor will have the equivalent view. And once you get into more details here and you start playing with your file system, you can use the utilities here in the data inspector to read it as different things. right? You could see that, okay, as a uint, it's this thing, as a character, it's the other thing. Okay. Let me close this. So I hope this is clear so far. Now, next thing that I'm gonna show you is a tool that I've been developing, and it's gonna be released in the next few days once I can get it compiled for everyone and stuff. This is gonna help you in the development of your file system. This is more as a verification tool. It will never do any writing for you, but you could always use it to verify the contents of the thing you wrote. Yes, yes, Jonathan. That's the file system, but it has more things than just the file. If you read the project description, it says that you have superblocks, you have the file allocation table, you have directory, you have user data, you have the reserved data. Okay, because it's a full-fledged file system. It's an actual usable file system. This toy, you could barely use it. Like this thing it's not really usable. Okay, do you want to work or not? Anyway. Guess we'll have to use the executable directly. So this is the tool. Okay. And let me find the file. So with this tool, you can browse into a file. By default, it looks for memfs images with the .mem extension. You can change it to either image and bin, or you can change it to any other file you want. It makes absolutely no difference. So you can load any of those. If it is a correct file, it will load all of that stuff. Over here, it will tell you what it read from the two superblocks. So you can verify that your thing is reading the correct things or it's writing the correct things when you get into that. Okay, those values all come from the project description and how they relate to each other. It's not magic things that I made up. In the directory here, you can see the names. This box here, it denotes a non-character. So this is the 0 byte, but it could be any other byte, right? That it's not a character, a printable character, right? You can see the individual bytes in the two root blocks, super blocks here, if you want to. Okay, this is not working yet. You can look into the file allocation table. So I'm really hoping that this utility will help you understand file allocation tables. Okay, you can click on an entry and it will highlight it, make it this reddish color. And if this entry is pointing into another entry into the file table, because this is how file tables work, it will highlight that pointed to entry in green. Yeah. So right now in this empty image, we have one file. Ignore this, this is just a test. This file does not actually exist in the file system. It only exists in the directory, not the file system. So this is the file allocation table for the whole image. As the project description says, the file allocation table has 256 entries because your image is 256 blocks. Does that make sense? So each block has its own file allocation entry. If you look at this, the way it's laid out, it's the way the things are in the image. So from byte 0 to byte 512, you can find the backup superblock. Then you can find the user data. Then the system reserved, then the backup FAT, then the directory, then the primary FAT, and then the primary superblock. Okay, so the primary superblock is at the end of the MIM image. Okay, let's see how this is represented into the FAT table. So since the very first block is the backup superblock, it's filled. We denote filled with 0xFFFF. Again, all of that is in the project description. Then all of these are zeros because they are empty. And then you can also read it from here. So it says that where is it? So the primary FAT table starts at entry 254. Okay, let's put in 254 in here. Oh, would you look at that? It's another filled entry because the 254th block is occupied by something. In this case, the primary FAT table. The secondary FAT table, where is it? At entry 239. Let's type in 239. Oh, look at that, another filled entry. Okay. Now, all of these are one block in size. Let's look into something more interesting. Let's look at the directory. The directory is yet another file, but this time the directory is 14 blocks, not one block. So the directory starts at 253. Let's type 253. This is entry 253. Entry 253 contains the number 252. That means that the next block of our file is in block 252. Let's follow that. Block 252 contains the value 251. That means that the next block of our file is in block 251. You're gonna do that until you reach this thing, which is gonna point to 240. You go to 240, and this is the end of the directory file. The directory file is a magic file that tells you which files exist in this file system. And it's located in those 14 blocks. Okay. Is this clear so far? And this is the end of the directory. You can see another field entry here, which is this backup FAT that we are reading right now. And from your book, you know that FAT-related file systems, they have this table where they allocate points and they allocate blocks. And the way to figure out which blocks make up which file the file will tell you, so that you go to the directory, you find the file entry will tell you which block the file starts at, and you do this thing that we just did here manually, following the chain until you reach the end. Okay, and once you do that, you have all your file blocks. The file blocks are gonna be file blocks that belong here into user data. And this is how fat systems work. Now, right now I don't have anything in the directory. I will also, so as you can see, I have the decoding of the directory done. I don't have the demonstration of the directory done yet. Okay. So once we go over that, once I've finished this demonstration here, I will release the tool to you. And while you're developing, you should be able to, follow along and play here to actually understand the fat table. No, the superblock is the superblock. Okay, the fat table is the fat table. They are different things. The superblock is how you start reading your file system. You first to verify that this is a file system that you can read and all of that stuff. And then the fat table it just tells you where files are to allocate them. And then you have to go bring those blocks to make up the actual file. Now, this was a very quick overview through the file system and how it works. There are way more details in the project description, and the reason I'm getting and I'm reading all of that is by decoding those structures that we saw. So in the project description, it says that, okay, this is at offset something, and this is the other. Okay. The directory for this file system, it's just a phone book. Okay. This file system does not have folders. It does not have directories. It's clear. This file system only contains individual files. It's a completely flat file system, similar to a memory card. Okay, your PlayStation 1 memory card, it was using this, a bit modified, but it was using exactly something like this. Your PlayStation 2 memory card, same story. Although the PlayStation 2 memory card, it could have nested directories. It wasn't a flat file system. Okay, this directory here, for the purposes of our system, the directory is just a phone book that contains records of what files are in the file system. Okay, so anything else? Any questions here? Anything else you want me to go over again? Otherwise, we're going to move into the VM and a bit of Fuse stuff. Fuse is very simple. Okay, so we are gonna go for that now. I'm gonna leave this open just in case. But first, let's go back to my drawing board. Okay, Um, so you probably have heard on Linux that everything is a file. Okay, and there is a very good reason for that. That's because Linux provides VMUFS, which is the virtual file system. VFS, sorry, not VMUFS, VFS, which is the virtual file system. Okay? And this is an abstraction over, let's say, file systems, but it has evolved over to an abstraction over everything. So everything in Linux knows how to talk to VFS, the virtual file system, and then you write programs, modules, drivers, whatever you want to call them, that can translate from individual things, usually file systems, but not always, and that can translate from these things into VFS, and then from VFS you can move the data over to your operating systems and applications and stuff. Now, why I said usually file systems? Let's say you have a graphics card. In order to talk to your graphics card, you have to talk to that driver. The way you talk to that driver is by writing to specific files. So you go through the VFS. You have something that looks like a file, but it's not really a file in the sense that we understand it. Okay, you read and write to that file. So you use VFS to read and write to that thing that looks like a file, and then whatever you read and write are translated through the driver into actual GPU commands that are executed in your graphic card. Okay, and that goes for everything. Your hard disk, same thing. Your USB. So if you have a USB flash drive like this one, okay, if you have this thing here, when you plug it in, there is some program that knows how to read the file system of this thing, which is, I believe, NTFS right now, and it's translated through that driver to VFS to finally Linux to be able to show you files and whatever else. Okay, so you have Linux. Similar things for Windows, but since you're going to be developing in Linux, I'm not going into any Windows details. Linux sends data and receives data from VFS. Okay, and now from VFS, you have your plugin architecture. So you have your NTFS, your EXT, your NVIDIA GPU, okay, all of that stuff that go back and forth here. Okay. Now, where Fuse comes in is that Fuse is yet another of those things down here. Okay, all of these are part of the kernel. Okay, so Fuse is hiding here in the corner. Okay, Fuse. It's a kernel module that once you install it and activate it, it is able to do user calls to talk to your program. Now, you know system calls. System calls are ways for an application from user space to ask the operating system to do something, for some utility, for some information, for whatever. There is an opposite thing for the kernel to call a user space application to do something and notify it of something. So Fuse does that, and when you have a Fuse application that we will see how to, Linux makes a call to VFS. VFS goes to Fuse. Fuse will go back to your program And at that point, Fuse will ask you a question. The question will be, what are the stats of this file? What files are in this directory? What's the size of this file? Stuff like that. Okay? That has been already translated through the VFS. So your job is to answer that question through Fuse. Okay, so your job is to say, this directory has files A, B, C, D. The size of file A is 10 bytes. The permissions of file A is this, this, and that. Okay? Now, the program that you will be writing just answers these questions. In order to answer those questions, you need to be able to understand and decode the structure of the file system that you're using. Does this make sense so far? So this goes back out, and this right now is your application that knows how to read MemeFS. This one had a slight stroke over here. Okay, does this make sense right now? At least conceptually. Yes, that's all the file systems are doing. Fuse doesn't know how to read. You know how to read, I'm hoping. Okay? All you do is you read the image and you convert that into something Fuse understands, and Fuse will convert that into VFS and whatever else. So, as I said, when you plug your USB in and you see 10 files in there, your operating system doesn't know about your USB, what your USB is doing, and honestly doesn't really care. There is some driver that will read this, figure out what the hell is going on with this, and then convert it into data your operating system can display to you, like file names. Okay, so in the project description, we have given you quite a few examples from Fuse. It's their own examples. And where is my VM? Here. Okay. So let's open up this directory. Now, for Fuse, you need a few things. If you use one of your old kernels, you need to make sure that Fuse support is enabled. So if you do the xconfig step and you search for Fuse, you will see that the kernel needs to enable support for it. If you do not have that enabled, you cannot use Fuse, even if you install what was in the project description. Vanilla versions of the kernel have that thing enabled. Your version of the kernel, if you go and use it, might not have it, so you need to enable it. Okay? Now, once you enable Fuse and you install everything that the project description says, actually let me bring up the examples really quick. Okay, here it is. And you install everything, you need a way to compile Fuse. Well, a program using Fuse actually, not Fuse itself. This is the makefile that I gave you for project 3 part 1. You can also go use the part 1 makefile, the project 1 makefile. You can use any of the makefiles we have given you so far. The only difference is that you need to add this line here. Okay, this line and this line. That's all in the Fuse documentation. Be very careful of the backticks here. Those are backticks. It's the button that's on the left of the one on your keyboard. They're not single quotes, they're not double quotes. They need to be backticks. Can you go over what Fuse will understand really quick? No. That's part of your job and your research. But Fuse understands VFS. It understands that someone asked for readme txt. Now, how you get readme txt out of your file system, that's your job. That's what you have to do for this project. Okay. Yes. Fuse acts as a translator between VFS and yeah. The main point of Fuse is that you can do all of this in user space. You could just use VFS directly, but if you recall, VFS is down here in the kernel. And kernel means long compile times, means copying from user space, doing stuff, right? It's a pain. Yeah. So the way you make your program is you need a standard C file, you need your main. It's very important to add the argc and argv parameters. Okay, if you don't, you're gonna have a very bad time. And then the next thing you do is you go through the examples we've given online. It's on the project description. Okay, you will need these two things. You definitely need to define which version of Fuse you're going to use. I have no clue where 26 comes from. It's in their examples, use it. And the Fuse header. In order to make one of these things to connect with the module in the kernel, you need to call Fuse main. Okay, with argc, argv, and for now we're gonna leave those two as null and null. This will not work. Okay, Fuse main will start this process of moving messages from VFS to your program and from your program back to VFS and all of that stuff. Now, Fuse main, you can just F12 this thing and read a bunch of stuff. You can read the Fuse the documentation online. That's part of what you have to do. Command line options. A very important command line option is -s. If you add this option, in essence, every call that happens in Fuse is atomic. It's locked with mutexes. That means that you do not have to implement synchronization yourselves. But it's also not going to be the most performant locking. If you want to, you can skip this and implement synchronization yourself. Okay. It says a bunch of stuff, right? For a single-threaded vs multi-threaded loop, you need to go and read all of that in the documentation. I cannot cover Fuse itself as a whole, right? Obviously, and I'm not going to. The next thing, so right now I'm just copying from the hello example, and I'm using the high-level API. There is also a low-level API that might make more sense to you. That depends completely on how you think about stuff and how you approach stuff. Okay, so go look at both examples. The next thing you want to do is define those Fuse operations. Fuse operations are, oh, it's a standalone thing. Nice. You have the documentation here for all of those, but they are mostly a copy of the VFS operations. Yes, high and low level do the exact same thing in a different way. Okay, so one might make more sense to you, so use that. I am using the high level API right now because it's easier to just copy stuff from. Okay, both APIs fulfill the same purpose, just in a different way. And Ezra, do we need to use the S? That's up to you. Okay. You can tell us that, okay, you have to run this with the S parameter. You can also modify argv, make a copy of those and force it there. You can have a fixed argv, right, and pass that into here. Right? That's up to you. Part of argv though needs to be the mounting point, which we'll get to soon enough. Okay, so your program should accept the mounting point as a parameter. Then you can add it into a different array. You can do whatever you want with it. Okay. Now, the next thing you want is the Fuse operations. Fuse operations, as I said, are a copy of the VFS operations. And as you can see, there is the read operation. There is the open operation, a read dir, read directory operation, and get attribute operation. Those are all function pointers. So pretend we have these functions here. We are gonna give as an argument, actually let me see the arguments again. Okay, so we are gonna give a pointer to this struct here. It doesn't have to be statically allocated. It doesn't. You can create it dynamically however you want. That's not. This is not the only way to do this thing. Right? You might have an easier way doing it with another approach. Right now, this is what's in the example, and this is what I'm copying. So we can explain what these things do. Do you need synchronization in this project? Yes. Whether you implement it yourself or not, that's your choice. But you need to have synchronization for this project. Because it's reading and writing into files. You cannot do things without synchronization. Okay, so as I said, all of these are function pointers. Let's look into this one. It's a function pointer that returns an int and accepts a string and a stat structure, both pointers. Okay, read link. All of those are, standard things. This is the things that VFS defines, and you need to fulfill these contracts, basically, fulfill these requirements in order to be able to be, in order to be compatible with VFS. So let me copy the rest of the functions. Okay, so this is their hello example. As you can see, it's returning minus an error code. Usually, user space stuff set the value of Erno. They don't return the value of Erno. Because, though, as I said, this thing will go back through the kernel and end up in a system call. You need to return Erno values, negative Erno values, just like you did for your system calls. Because this code will eventually be called from a system call. So you still need to fulfill that contract. Thankfully, you do not have to do copy from user and copy to user and all the user access and all of that stuff. That's taken care by Fuse for you. Okay. So we have these four functions. Read reads from a file or from a directory. Open opens a file or a directory. Read dir reads a directory. Hello get attribute gets the attribute. This is the results of stat. If you do an ls, LA, all of the data that comes along, all of that stuff comes from get attr. Okay, they check here. So this file system has one file called hello, and the contents of that file is hello world. Okay, this is the entire file system of the example. So let me make this thing. Okay, it's built as hello test. And now I run hello test and I need to tell it the mount point. I need to tell it where this file system will live. It can be anywhere. Okay, it doesn't matter where you put it, as long as it's not inside another MEMFS file system. Okay, so you can put it anywhere, and you need to have permissions in that directory. I have made a directory, my hello dir. You could put it in, I don't know, home, username, potato. You can put it wherever you want. Okay. So my hello dir. Ooh, it says it's not empty. Okay. We are going to unmount the file system that is already there. And you do that with fuser mount or fuser mount or whatever you want to call it. That's U for unmount, and where I mounted the file system previously, that's done. And now I'm going to mount it again. And now if I do an ls, lay my hello directory, as you can see, I have one file called hello with some attributes. All of these attributes are coming from the get attr function here. So when I called LA basically called all of those functions with the exception of read. LSLA, called all of those. Okay, and if I do cat my hello, I'll get hello world. And this is the entire file system of this example. Okay. The way read happens is you can check here. It checks to see that the path that is requested is the same as the hello path. And then it does some calculations and copies bytes over. Okay. Now, this file system, as I said, has hard-coded values. You would want to do this programmatically. And how you do them, so for example in readdir, as you see, it gives all of the files that exist in the file system. It's dot, double dot, and hello. The way you do that is you read your directory, for instance. Okay? And you parse that directory. By directory, I mean this thing. Where is it? I mean this thing. And you figure out the file names, you figure out the sizes, you figure out permissions, all of that is stored there. And you return those values. Same for getAttr. Now, when you are implementing this thing, you might want to, here in your main, for example, read this file and store some metadata. Like you could store the directory itself, you could store the file table itself in memory. Okay, so in this program, in the hello.c program, you store in that memory contents of this file, so it's easier for you to later parse it. You can also mmap this whole image and read the bytes directly. You could read it byte by byte every time. Whatever makes sense for you. Reading it byte by byte every time, though, it's gonna be the most time consuming and it's gonna involve writing a lot of code and repeating a lot of code for probably no reason. But if you cannot wrap your heads around the other approaches, you can always do that. That's fine. It's gonna be slower, but I mean, okay, the design of how this translation now happens is up to you. You probably want, as I said, to store some stuff, and you do that by creating structures and populating those structures from the raw bytes of the file and keeping those structures in memory. So let me do this. Actually, I'm not going to do this. I'm going to do it this way because this is the name, potato.txt. And here in readdir, I'm going to call this function again to give it another name. The name is potato name. And now this argument is a stat file pointer. You could fill this thing in with the results of what you would get here in getAttr if you really wanted to, and skip this call. If you don't, VFS will do this call again for you. So it will ask you again for that specific stuff. So I'm putting this thing here, okay. Remember, to unmount, you do F user mount and where you mounted this thing. Compile this program again. Why is it complaining? Okay. Yes, it is used. Oh, I didn't save it. That's why. Compile this program again, run it again. Let's put it in the same directory. It can be whatever you want again, as long as you make that directory and you have access. And then if I do an ls on my dir again, as you see now, there is yet another file called potato.txt, which is read, and VFS has no idea about its stats because I never returned those stats. And here, I'm not returning any stats about it. This example doesn't relate to the file system we're using, right? This example is about how you use Fuse. Figuring out the file system is your job. Documentation will explain most of this stuff. It does. Nlink 2, I think, is for directories. Right. Again, you would have to do all of these with logic instead of hard coding those things. Okay. And yeah, this is Fuse. Literally, you define some functions and you answer the questions. And you can find the questions by going to the website. They have documentation. You can search, okay, I want to see what Fuse operations are. Open up the Fuse operations in the website. Read what they do, read what all of these things are, and that's it. They have more than enough information for you to do that. Are there any questions? Anything you would like to go over again? Scene 1 plus 1 for hello path. As you see, the hello path is defined with a forward slash here. So plus 1 will start from 8. We'll start the copy from 8 instead of the... because this is not part of the need. That's why I didn't include it here. Your file system, MIMFS, does not support, nested files. So there is no need for these things. That's why I didn't include it here. Oh, also, you should always include these two files in any read dir request, because dot and double dot is always present. And filler is just a function, it's a callback that will go. You need it because the name of the file is hello. It's not forward slash hello. If I remove it and let me unmount, and let me mount again and do an LSLA, as you see, it broke because forward slashes are not part of a name. They are part of a path and they separate parts of a path, but they're not part of the name itself. I don't have the hello. That's their example. I just copied their example. Okay, this is their example because while reading your stuff, it might come through with a slash for some reason. You need to make sure that you're not giving that slash. Yes, Jonathan, with one difference. Your file system does not have directories. It does not have folders. Okay? Your file system does not have folders. It has files only. The directory thing in the project description, as I said in the beginning, is just a phone book of files. Yes, you just list the files that you have. A rate dir would be is a very simple function to do. Because there is a parent directory. There is always a parent directory. That's why you need the double dot. MemFS does not have a nested directory, so there is no directory inside the file system, but there is always a parent directory, which is where you came from. In this case, since I mounted it here in my hello dir, the parent directory is just forward slash, so it's just the root. No, it's not the one containing the memfs image, it's where your file system was mounted. So when I run this, let me bring this up. So when I run this with hello test, my hello dir, the file system, this weird file system in the example, is going to be mounted inside my hello dir. Okay? The parent of my hello dir is, so from here, if you remove my hello dir, you get forward slash, the root. So the parent of my hello dir is the root. And since your file system is mounted inside my hello dir, the parent of your file system is the root. If I were to mount this file system inside slash mount memes, okay, the parent of my file system in that case would be slash mount. Right? It would be this thing. Yes. Yes, that's true for any file system. That's part of VFS itself in Linux and Windows by extension. Dot is the current directory, double dot is the parent directory. You always have a current directory and you always have a parent directory. The only exception being the root directory, where the parent directory is this directory. And you don't have to deal with that anyway. That's not part of what you have to do. But literally any other directory has the current directory and the parent directory. Yes. correct, Jonathan. The fuse part, it's just about reading data from your image and passing them back to Fuse in a way that Fuse understands. So if we go back to here, in this example, this image, I have one file called myname0.txt. Now, whether you want to maintain that zero or not, that's something that you have to take a look at. You probably don't. So, in essence, you would just copy, you would call, where is it here? You would call filler. What? You would call filler with my name. Wait, no, it's like that. It's not my name txt. And you get my name txt through parsing the directory and stuff like that. See, do I mind summarizing the diagram? Okay, so for those that were not here due to YouTube, really quickly, this diagram is you have Linux, the operating system itself. It's communicating with VFS for everything, basically. And VFS is the virtual file system. This is how files are represented in Linux. All the inodes and the D entries and all that stuff, they are part of VFS. And then you have plugins that know how to convert from something specific into VFS. So you have a plugin that can convert from NTFS, which is the Windows standard file system, into VFS. You have a plugin that can convert from ext4, which is the Linux standard file system, the Unix standard file system, into VFS. You have another plugin that can convert from your graphics card into VFS. And then you have Fuse, which is a module that can use user calls, the opposite of a system call. Fuse makes user calls to your program to ask it questions, gets that data and moves it back to VFS, which will move it back into Linux. So when eventually you go into here, when I did the ls part to see the files, this is how it happened. Let me see if it will work with. Wait, what? I have a feeling that my file manager is gonna break when I go to there. So root my hello directory. Yes, it broke. Because we had that directory thing that we're doing here. So unmount, make, whoops. Make, mount again. If I go back and back into here, now you can see, I can see the hello file. I cannot see the potato file because I do not have any stats for it. Let me see if I do a Control-H. No, nothing. And if I open the hello file, it opens up with a text editor because there is nothing around it. And it contains hello world. Now, I think that if I try to save it, it's asking me for a password because I cannot save. This example does not support saving. Okay. That's it. So your next steps would be either to understand Fuse or the MIM file system. Pick one, start there. And once you understand one, you move to the next, to the other, and then you try to combine them. If you start your project, okay, how do I do this project? You're gonna have a very, very, very bad time. If you want to start with understanding the file system, make a program that just reads the image and tries to extract values out of there. Try to extract the signature, then try to extract the whatever else is in the superblock. I don't know. Once you do that, try to put all of those in a structure. Design that structure. That's up to you how you design it and what you put in there. Okay, and move like that step by step. If you start with, okay, I want to read file, yeah, what is it? Here, I want to read file my name txt. You're not gonna do it. I'm not kidding. You're not gonna do it, or you will waste all of your time trying to do that and end up not doing anything for the project. Start by understanding what you have to do first. Yeah. If there are no more questions, I guess I'm gonna call it. And make MimFS just makes an empty file system that you can use to read. Once you read, you will have zero. You will have no files in there. Now, we did make one image that contains one file. Not this one. The one that's on screen right now is a fake. For my testing purposes, we have an image that we will give you, once we release this tool as well. But for right now, you do not need it. Just make an empty file image using make MimFS and see if you can get the data you want out of it. And by data, I don't mean the individual file. I mean, start with things like, where is the FAT table located? Can I see it in the data? You have your hex editors to help you. Do I have Octeta here? No, I do not have Octeta installed in this VM. Is there any other thing? No. But you can just Google and find various things, various hex editors for your use. What do you mean that they are defined by the offset? I don't think I understand the question, Ezra. Yes, the default kernel 4.19 or something should be enough. Can we reference each part by its offset? There is always an offset, but the thing is that you are in control. That's what I mean by understanding the file system. Okay, you have a bunch of bytes, and you need to see how you're gonna read those bytes, just like we did in the initial example. Offset there was just an idea. It was just a concept that, okay, I need to move this thing somewhere to read. Sometimes that somewhere can be hard coded. Sometimes that somewhere can be computed. So you are in control of that. Now, the structure, by structure, I mean literally a C struct. All right, so struct my struct. Okay, I mean something like this. You can put whatever you want in here. It's your design to make, whatever helps you. It can be data extracted from the image directly. It can be data that you compute through the things you extracted from the image. It can be other data that you found out you need, and you need to keep track of those somewhere, and you put them in a structure. You are in control of that. You can design it however you want. And as a reminder, I said it earlier, you can also mmap the image file and use that instead of using fwrite and fread. But that's up to you, whatever makes sense to you. Try both approaches, see which one works best for you. Uh, Random space fillers, yes, there are bytes like what you describe. For alignment purposes, they are also clearly defined in the description. So let me see CE. A quick example, I think, is in the one I remember right now is in the timestamp. What is the timestamp here? Oh wait, I lost it again. Ugh. Okay, so the timestamp is 16 bits, so 2 bytes. And it says that, never mind, it's 8 bytes. Yes. So it says that the first byte is the century, second the year, blah, blah, blah. The 8th byte is just 0. There is no purpose to that byte other than data alignment. That's it. When do you need to use the backup FAT? If the main FAT is corrupted, you need to go to the backup FAT. Yes, Jonathan, that's what I said. Your starting point is either understanding the file system and making a program that just reads values out of it, to see if you can read them, and then maybe put them in a struct to start working with that and playing with that. Or your other starting point is starting with Fuse with a stupid example like this one or one in the examples list. They have more complicated examples. You start with those and you start modifying things to see what happens. Okay, so what will happen if I change this to 755, just like the one above? Do that, compile, see what's changed. Okay. Just pick one of the two, whichever one you want, and start there. You could also start with one, do a little bit of work, then move on to the next one, and then go back to the first. That's fine. Okay. Are there any more questions? I'm just waiting because, delays and everything. Some people were 5 minutes behind. The size is defined in the set. No, it's the other way around. This thing here, the project description tells you how the system is set up. You use this to read the bytes, and you use those bytes to populate your structure. The only reason you have that structure is so you can put it in a reasonable format so you can use it easily. For instance, there is, let's say, the superblock that you mentioned. It has the version number of the system, which is 4 bytes. You would you rather have this thing? Where is it? Let me go back to the code. Okay, let's say that this is the superblock. Would you rather have something that's called version? Sure. And be able to do superblock dot version. This is a version. Or would you rather go to the file every time, navigate to that offset, and read those 4 bytes every time you want the version? You probably want to have something like this because it's obviously easier for you to use in code. And you do this by when in your main here, before you call fuse main, you just open the file and you read it. Not necessarily all the parts, but some of them that you have to keep reaccessing frequently, yes, you would have to move them into structs. Because then it is also easier to write those structs into the file. Like look at make memfs, the program that we gave you. It creates a superblock structure, it populates it, and then it writes those bytes. It doesn't write random bytes. Okay. Yes. Yes, fat and fat size, the start and the size and all of that stuff. It tells you how the file system is laid out. If you recall, there are some reserved blocks, 18 reserved blocks. You could modify that file system to use some of those 18 blocks for data purposes, for instance. Or it could move a secondary part of the directory there. I don't know, for reasons. Now, when you are parsing it, you could verify some of these things. So, for instance, when you read that comes into the backup blocks as well. Let's say you read your primary superblock, and it tells you that. Actually, let me see the actual numbers so I don't make a mistake. So, you read your primary superblock, and it tells you that the user data area is 230 blocks. You're like, okay, let me read the backup superblock. The backup superblock also tells you that the data area is 230 blocks instead of 220. You can, at that point, it's your choice. Do you run with it and your code adjusts for it, or do you exit because the image is malformed? It's not formatted properly. For this specific example, you could very easily adjust for that. And your driver should still keep on working, even if there are more blocks than you initially expected. There are other values that you cannot adjust for. You will probably find them while working with the system. There is no data in the superblock. Well, do you mean file data? Then in that case, no. There is no file data in the superblock. But there are data in there, yes. Yes, so no file will be in the superblock. The superblock itself is a file. You can think of it as a special file. So this thing and this thing are special files, and in fact, so are the directory, the FAT table, and the backup FAT. As I said earlier, so backup superblock, the first entry is one block filled. It's also filled here. This thing is this thing. Then we have the user data, which is dynamic almost. System reserve. Then you have the backup FAT, which is at, what is it? 239. Yeah, I'm not gonna do it this way. Here it is. It's also filled. And so on for the rest of it. Once you get our image where it has some of the data filled, some of those zeros will also be filled, pointing to a chain inside user data. Each user block is just going to be raw data. Now, the file itself, let's say you store a PNG file in there. The PNG file has some headers, but that's part of the application reading the PNG. It's nothing MemeFS related. The headers, all of the headers are in essence in the directory, in this directory, and in the FAT table. Everything in user data is just raw bytes. What do you mean it's section? What is a section in this context? All of that are in specific places in the project description. Let me quickly see something. Okay. So I cannot find the actual comment right now, but I do have a picture of it. This is the layout of a properly formatted meme file system, of a proper image. This is what the make thing generates. And the numbers here are in blocks, not in bytes. So byte 0 at the beginning of the file is the backup superblock, not the actual superblock. And at the end of the file is the primary superblock. And it's one of those, its block is 512 bytes. So this is 512. This is 512. This is 512. This is 512. This is 220 times 512. Right. And on and on. Right. It seems that we are well, basically out of questions. We're done right now. So I think we should call it. It's like 2:35. Well, I've already explained it twice in this stream, and it's also explained in your book and in the resources we've given. So I'm gonna direct you there. Okay, I'm not seeing anything else coming up. So, yeah, I'm gonna call it. Good night, everyone, and see you next time.